Hey folks, nice fall day in the backyard of science. Pretty warm out really, but it has that little cool edge to it. Got my cup of tea here. And I'm thinking about how this tea is going to cool down as I continue to hold it or as I drink it. I mean, eventually it's going to reach something close to the ambient or outside temperature that we're experiencing. Right now it's pretty hot. I just poured it. And that's got me thinking about the rate at which things cool. And so I thought today we could do a little experiment about how water cools. And so I've got a question in mind, and I've got some tools that we can use to figure it out. So let's go on and head into the shed of science and see what we can learn. Shed of science. So as my tea cools down, the question I'm thinking about is how long it's going to take it to reach the ambient or outside temperature. It looks like the outside air temperature in the shed of science right now is about 18.3 degrees Celsius. And my tea is probably closer to about 95 Celsius or 90 Celsius since I just boiled the water. So I can certainly put a temperature probe in there and see how long it takes to cool down. I'm also curious to know how long it would take just room temperature or closer to room temperature water to cool down. So the water in that Nalgene bottle there is a little bit warmer than room temperature, somewhere in between the tea and room temperature. And I suppose it'll eventually cool down and reach room temperature as well. Both things will equilibrate with room temperature. But I wonder if they'll cool at the same rate. If the tea and the closer to room temperature water will cool at the same rate, or will one reach the room temperature more quickly? So that's what I thought we could set up an experiment here today with our temperature probes. Let's jot down a couple notes on this, and then we'll set up the experiment. Okay, so here's the idea. We're going to have two containers of water here. We're going to use those flasks that we saw in the last video. And one of those flasks is going to have pretty hot water in it. Maybe I'll draw that flask with a red outline so we know that it's the hot water flask. And then one of those flasks is going to have, it's not a very good flask, but you get the idea, is going to have warmer water, but not quite room temperature water, somewhere in between the hot water and room temperature. So I'll draw that with the orange. Hopefully we can distinguish those enough. And so this one has a temperature that's somewhere closer to room temperature. We know the ambient temperature, the air temperature right now, is somewhere around 18 degrees Celsius. And I expect that the hot water flask is probably going to be somewhere around, I'll put 95 degrees Celsius. And I don't know what the middle one is. Let's just, for the argument's sake, say that it'll be somewhere around 50 degrees Celsius. What I'm curious about is how long it takes them to reach room temperature and the rate at which they cool. Now, we talked a little bit about rate of change and variation when we looked at the sound video when Dennis DeBay did that with us too. So I want to think now about how that looks over time. So we're going to set up our experiment to graph temperature over time as these things cool. Let's check that out. Okay, we've got our experiment going now. Let's see what we have. In the left-hand flask, we've got the hotter water, and in the right-hand flask, we have the cooler water. Now, they both have the exact same amount of water in there, 300 milliliters in each. You can see that. And the container is the exact same size as well. They're 500 milliliter flasks, and they have the same temperature probe in there. Okay? So the only difference there is the temperature of the water. The one on the left is hotter. Let's go over here and look at the setup on our data collection device. So I've got it set right now to record temperature over time for a couple of hours. We're going to take one reading every 15 seconds and it'll automatically graph it. And you can see the hot water container right now is at just about 82 degrees Celsius, and the cold water is at about 50, the cooler water is about 57.5. So we're going to let that run for a couple hours. Remember, the ambient temperature is around 18 Celsius. And we'll come back and look at this graph and see how the rate of cooling for each of those two different temperature waters compared. Okay, so our 2 hours of data collection is finished, And this is what our graph looks like. So our hot water started at 84.5 Celsius and our cooler one at 58.8 Celsius. And after that whole time, it looks like they almost converged at the same temperature. But some questions you could ask yourself is, what do you notice about the rate at which they cooled down? So they're essentially the same temperature now, but what do you notice about that rate? Now, there's a way we can quantify this. There's a mathematical description called Newton's law of cooling, which helps explain how these things cool down. But it's really interesting to notice that they do cool at different rates across different time intervals. One thing I notice is that the hotter water cools faster initially than the cool water, and then as they get closer to the same temperature, they start cooling at a similar rate. So I guess to answer our question, does hot and cold water cool at different rates? They do when the temperature difference between the water and the air, or the ambient temperature, is different. And so it has something to do with the difference in temperature between the water that's cooling and the temperature that it's cooling to. I'll show you real quickly on the whiteboard. Okay, so let's look at our graph that we had from the data collection device. The red dots represent the hot water and the blue the cool water, and you can see initially the hotter water cools at a faster rate. That's a steeper slope than the blue water was cooling, but then they kind of converge on each other, and as they get close to the same temperature, they start cooling at the same rate. Now, the equation which describes this is called Newton's law of cooling, and it's given down here. It's a pretty straightforward equation. It's not something you probably need to know, but just to explain it to you anyway, that we can calculate the temperature at any time t, small t is time, if we know a few things. One is the ambient temperature to which it's cooling. That's T alpha. So T with the little alpha is the ambient temperature. That's the temperature to which it's cooling towards, the room temperature. T0 is the initial temperature of the water. And there's an exponential here with a constant k and time. We won't have to figure that out, but that describes how the exponential is describing, the e to the kt, is describing this rate and how that rate changes as a function of the difference between the initial temperature and the ambient temperature. So the bigger that difference, like from the hot water to ambient temperature, the steeper that slope. And as that water cools, and as these two temperatures start to converge, then they have a very similar slope. So the bottom line here is that water cools at different rates, and it depends on the difference between the temperature of the water and the air temperature. Hot water is going to cool faster initially than cooler water, but as they get close to air temperature, they'll start to cool at the same rate. So that's our backyard science for today on cooling.